So we actually looked at some of the chemical reaction stuff in class, so I'm going to kind of skip over the slides that we did in class because we did this exact slide in class. Types of reactions you learned last year, these are the types of reactions we focused on this year. Balancing the equations, remember you always want net ionic. Where's my, there it is.
Hola.
Hola. Hi.
Hola, señor. This is a college class. Química.
I'll be right back. My mom just texted me.
So net ionic equations are always what you want to write. Right? Even if it says write a balanced equation, they still want net ionic. Just remember potassium nitrate, ammonium, sodium. And then your strong acids, strong bases. Those are your strong electrolytes. They break apart in water. We actually did this making prediction one already. We did these limiting reactant ones already. Okay. Some of the free response questions are going to start asking you to think about lab. So this is one. They're all going to be based on labs that we have done in class. We did this one. This may have been one of the very first ones that we did. The very beginning of last semester. You guys had to determine the empirical formula of copper oxide. And so when you're looking at experimental design, this would be a type of synthesis reaction. So a sample of pure copper is heated in excess oxygen. Design an experiment to determine quantitatively. Quantitatively means with numbers. Whether the product is CuO or Cu2O. So copper 1 or copper 2. So just some basic steps for this. The first thing that you want to make sure to do, find the mass. Right, your masses are probably going to change. Find your masses. Then you'll heat up the copper, that's what it tells you, until it stays constant. Because once the mass stays constant, well, why do we want the mass to stay constant?
It's over.
Then it's over, right? Then the reaction is done. Then we want to find the mass of oxygen. So we can just subtract. Because what is that? The law of what?
Conservation of mass.
Conservation of mass. And then compare moles. Always compare your moles. But if we compare the moles of oxygen to the moles of copper, that's going to give us our mole ratio. If it's copper 2 oxide, what's the mole ratio of this copper to oxygen and CuO? 1 to 1. If it's copper 1 oxide, it's 2 to 1. That's how we're going to tell whether it's copper 1 or copper 2. For decomposition reactions, they might say something along the lines of design something to show that calcium carbonate proves the law of conservation of mass. Well, what's going to be the big thing with this decomposition reaction? What it splits up into, we have a solid, but what else do we have?
Gas.
A gas. So you need to make sure that somehow you collect the gas. Because what happens if you don't collect the gas? You're going to lose it into the surroundings. Okay, so we can find the mass of calcium carbonate. We want it to be in a sealed container. We can heat it up, find the pressure that gets us our gas, and then we can find that the mass of your CO2 plus the mass of your calcium oxide is going to give you the calcium carbonate. Another one with data analysis. They're also going to ask you to analyze data. That's why I have you guys do that in labs, right? Like sources of error or what happens if there's impurities. You might be given something like this. You have mass of pure tin, the mass of the crucible, crucible plus the oxide after second heating, after third heating. If you have a hydrate like this, right? Or you have some sort of compound. Again, what's the significance to heating it multiple times? Yeah, take a look at the mass. You're going from 0.5 to 0.25 both times. So you're probably evaporating if there's water or any kind of gas. How do we know that it's probably done after the third heating?
Because it's very similar.
Right, it's very, very similar. So this is how can you use this data to determine the formula of the product. So this is just showing step by step what we just talked about with copper 1 versus copper 2 oxide. You're just comparing your mole ratios. So just some lab-based questions. If they give you something with lab data, you're probably going to be using it. Acids and bases also followed the chemical reaction. So we did acids and bases yesterday?
Yes.
Today.
Yesterday.
Bronsted-Lowery is really what we focus on, right? Conjugate acid-base pair. Don't forget that amphoteric is a thing, right? Acts is both an acid and a base. And then redox. Okay. Electrons are transferred during redox. Whether you remember Leoger or oil rig, right? Think about electrons. Yeah, and then when you're thinking of cells, okay, red cap, reduction's at the cathode, oxidation is at the anode. So anox, red cap. When something is reduced, it's gaining electrons. You always want to do half reactions. Okay, redox. How do you know if something is a redox reaction? Oxidation numbers change, right? Probably is going to go from 0 to something else. But always split it into its half reactions. That way you can tell what is being oxidized or what is being reduced. Okay, so question like this. Zinc ions will react with aluminum metal according to this chemical equation. Based on this chemical reaction, how many moles of electrons would be transferred when 1 mole of Zn2 plus ions are consumed? So talk to people around you. Do some stoic. Okay, this one's going to be C. Okay, because the question specifically says 1 mole of Zn2 plus. Okay, this is 3 moles. Here's a way you could think about it. Up here, how many electrons are being transferred in this balanced equation up here? How many electrons would you need on the left in order to balance this charge out?
Oh, wait, that's
6, right? 6 electrons are being transferred within this entire thing. That's how many you'd have to cancel out when you combine these. Well, you have 6 moles of electrons for 3 moles of zinc. We don't want it for 3, we want it for 1. So divide 6 by 3, that gives us 2. Okay?
I'm sorry. I was trying to put you forward to see
Sorry. You guys also did redox titrations. Redox titration, okay, remember that redox just stands for oxidation reduction. I heard some people saying that it was like reduction and redox. Like, no, it's oxidation and reduction, you combine it, that's how you get redox. But when you do redox titrations, the whole point is still to figure out the concentration of whatever is in the flask. You guys used hydrogen peroxide, and then used potassium permanganate. Potassium permanganate has that distinct purple color. And then eventually it's going to turn the pink color once the reaction is over. When you are discussing redox titrations, really the biggest thing is that you want to talk about, permanganate is purple. You actually didn't even need an indicator down here. Because this stays colorless, while MnO4 minus gets reduced to what? Mn2 plus, right? So MnO4 minus gets reduced to Mn2 plus because it's acidic. Right? If it were basic, it'd be MnO2. But because this were acidic, as this gets reduced in the hydrogen peroxide, it stays colorless. Once we're out of hydrogen peroxide, though, permanganate's no longer going to be reduced, and that's what turns it purple. Okay, then they always like to ask questions about providing evidence. Okay, so one might be evidence of a chemical change. Well, ways you can tell is you make a gas. How do you know that you've made a gas? Bubbles. Okay, you form a precipitate. Maybe you change color. Okay, if you add lead 2 nitrate and potassium iodide, you get a yellow solid. Lead iodide is yellow. Or production of heat, or maybe the absorption of heat also is how you can tell that a chemical change has occurred. Remember, chemical change and physical changes are different. I don't even think we talked much about physical changes this year because we did it last year. You might see something making bubbles during a physical change. Example? Boiling water. Right? Boiling water, you see bubbles. But are you actually changing the water as you boil it?
No.
No. Okay, please remember. Please, please, please remember that boiling water does not break covalent bonds. Okay, boiling water is breaking hydrogen bonds. Okay, you're breaking hydrogen bonds, you're just breaking the intermolecular forces between the molecules, not within. Okay, changing energy is also in big idea number 3. We talked about energy today, but you have exothermic versus endothermic. When we get into kinetics tomorrow, we'll look more at activation energy. But remember, activation energy is the amount of energy you have to put in. If you have to put in more energy than you get back, that's endothermic. If you only have to put in a small amount and you get a whole lot back, that's going to be your exothermic. Remember that bonds broken are endothermic. You have to break something. If you form the bonds, those are exothermic. Some stuff with galvanic cells. I wrote some stuff down because I was listening to more of that video about cells. The AP test will use the term galvanic instead of voltaic. They're the same thing, but you will see the term galvanic instead of voltaic. Remember batteries. Okay, batteries are galvanic cells. They run on their own. They run spontaneously. If they run spontaneously, what does that mean about their equilibrium constants? Yeah, it's going to be greater than 1. It's going to be big. Now, I will tell you that galvanic cells have extremely high constants, like times 10 to the 75th high. That's why they're so spontaneous. Galvanic cells do not exist at equilibrium. If a galvanic cell is at equilibrium, its voltage is 0. You don't want it to be at equilibrium. It will die. It will actually die because it has no more voltage. So at equilibrium, the voltage equals 0. Don't forget, you can compare cell potential to the equilibrium constant through delta G. You have that on your equation sheet. Delta G equals negative NFE. Delta G also equals negative RTLNK. So you can put them together and have NFE equals RTLNK, and you can compare the two. The closer to equilibrium that you get, the lower the voltage becomes. Right? Remember that batteries don't want to be at equilibrium. Okay, so the closer to equilibrium you get, the lower the voltage becomes. The further from equilibrium, that's better. Further from equilibrium, the higher the voltage. Okay, so those are just some things with galvanic cells. So, bless you. So here's a question. The following is based on combining the 3 half cells listed below. So we have tin, silver, chromium. Okay, X, Y, and Z then. What is the cell potential of galvanic cell Z? So cell X is 1 plus 2. Cell Y is 2 plus, this should say 3. 2 plus 3. And Z is going to be 1 plus 3. You're trying to figure out this potential. So work through that with people next to you. See if you can find the cell potential of galvanic cell Z.
Need a telescope back here this morning.
I got my glasses.
No, you don't need, you're saying reduction potentials?
Yeah, don't you need those?
Because they give you overall cell potentials right here. Like this is all.
It would just be...
Hey, give me telescopes.
Well, you know there's lots of seats up here.
I'm just counting fast on my jaws. I'm like, a lot. That's what we need in this car. Give you footsteps.
Pick it up. That's all come down. Okay. So for this answer, the correct answer is going to be B. Okay. Essentially, what you're doing is you're doing Hess's law. You're doing Hess's law with cell potential. Okay. You want to get this reaction. Now, I will tell you this. Remember, whenever you multiply, you flip. There's only one thing that you can do with cell potentials, and what is that? Change the sign. That's it. Don't do anything else with cell potential except for change the sign.
Oh, that's a little bigger.
Okay, so then here's another one. It's the same data, so in case you forgot, cell Z has a potential of 0.6, just in case you forgot. In galvanic cells X and Z, which of the following takes place in half cell number 1? So in X and Z, which of the following takes place in half cell 1? So you should be focusing on what actually is in half cell 1. But you're trying to label. Okay, right answer is C. Because half cell 1 is 10. What's happening to 10 in X? 0 to plus 2. So that is
oxidation.
Oxidation. And then in Z, you're going from plus 2 to 0. Okay. It's being reduced. Okay, so that's actually it for big idea 3. Now, I do want to show you something. Hang on. Kinetics is tomorrow. Is that what I want? Oh, yeah. Okay, I want to show you guys this. This is another PowerPoint that we're actually not going to have time to do on like one of the days after school because we only have 6 days. This is posted online though with Big Idea 6, and I just want to kind of show you how it works. Always, if you want to play these are on the website. Download them. So instead of just viewing it on Google Drive, actually download it and then play it in slideshow mode. Because as I go through, right, as you click, notice like the visuals change.
Whoa.
Well, if you do that on, just like you should look at it on Google Drive, all you see is this. Actually, this is what you see. So it doesn't actually even go through the whole thing. But what this is doing is this is showing you lab info because there will be questions on labs. We've done all of the labs that you will be tested on. Like gravimetric analysis, we did at the beginning of the year, toward the beginning of the year. But like gravimetric analysis is how you determine percent composition or maybe empirical formula. It's when you, well, take a look at the steps. You dissolve, you add to form a solid, then you filter, and then you can use your masses, you can find an empirical formula. You guys did it with, I don't remember what you did it with. But remember to go to moles. Now, these are the types of questions that they're going to ask you. You know, possible sources of error and how they might affect your results. So, for example, if you had contamination in a solid, your mass would be too big. Right? If your precipitation didn't go all the way, then your mass would be too small. Those are the types of questions that you would be asked. Gas cell labs. See, this is how these PowerPoints actually work. Determining molar mass. I don't know if we got to determine molar mass this year. I think we did it last year, though. But see, like, it's all going to go,
Pivnert.
right? So here's what you're going to do. You're going to use Pivnert. Then, if you want to look at molar volume of a gas, that's over here. You guys did this last year and this year. Well, you should have done it last year. We had HCl up here, magnesium. Hydrogen gas went up. You collected the hydrogen gas over water. Don't forget, you collect a gas over water. Total pressure is water vapor pressure plus the pressure of the gas. And then we talked about Graham's law. We talked about this demo. Which of these gases moves faster, NH3 or HCl? NH3, why does NH3 move faster? It's smaller. Travels faster, that's why you get this solid right here. They asked, this was a multiple choice question last year. Because they came in and they were like, Miss Carney, you're never going to guess. That was a question. Oh, shocking.
Never gonna guess. Did you guess?
Yeah, I did guess. So, here's a multiple choice question. A sealed gas cylinder has a mixture of 3 gases. If the total pressure is 100 millimeters mercury, what would be the partial pressure of neon? I'm going to tell you, when you're given problems like this, do not overthink it. Okay? Neon makes up how much of this mixture? 25%. Notice, you don't get a calculator on this. They make it easy for you.
Thanks.
Thank you. Ooh, sure. And a card.
Happy new shirt.
That's what I'm wearing. Don't have to do laundry. I'm just kidding.
What if like we came and just wearing it like for the rest of the week, like tomorrow, Friday, Monday, and we're just like, Miss Carney. Save it for the AP test.
We should have made shirts.
Pivnert. We want to make Pivnert shirts, and by we I mean just me.
I actually don't think that you could wear it to the AP test though.
That's so
I had to tell Jevin that he could not wear his periodic table shirt to the AP test last year.
Why?
Because they'd be considered cheating.
They give you a periodic table. But it's not the AP regulated periodic table on his shirt.
I had to tell you.
Isn't Pivnert the equation
What if
sheet?
those AP regulated?
You like it? Here it is. Or the equation sheet. Put the equation sheet on the front and the back.
We'll just be like, alright.
You need to make it upside down.
Yeah.
Make in 8th grade for geometry.
We would get bonus points for wearing a little cheat sheet on our shirts. We would get bonus points for wearing our geometries. They had all the formulas on it.
They
That's the only reason I wear them all day.
They had this party. They had all the formulas, and if you wore it the entire day, you got bonus points. That is the only reason why I passed geometry.
I put dots all over mine. I spent one day in gym and like all makes it a super rainbow.
That's just yelling at me.
It was sweet. It was sick.
It looks so cool.
It's like this.
Wait, chromatography. Yeah.
Alright, my work here is done.
Okay.
Bye.
So chromatography, like I said, I think yesterday, column chromatography could or could not be included. We don't know.
Look at what could.
Strong maybe.
Yeah, we did paper chromatography. Ours didn't look quite like that, but we did it. And then column chromatography as well. Okay. Like I said, the review book covers column chromatography. You just pack it with different things, and then the solvent goes through, and whatever it sticks to, that's, it's similar to that polarity. They're actually, as you go through this, you can actually click to watch different videos, do virtual labs. So this lab, PowerPoint's going to be super helpful. Then again, notice errors. You could just suck at doing chromatography, I guess. Synthesis. You guys did alum Friday. Yay. This actually is a big AP lab. Like, they love talking about alum. So good thing you guys just did it. Remember, you guys had aluminum. You didn't use foil, you used pop can. Possible sources of error were impurity in aluminum, like the plastic coating. What did you guys do to make sure that you didn't have that? Okay, so you sanded it first, And then after you added the potassium hydroxide, do you remember what you did? You let it react. It took like 25 minutes to react. What happened?
Yeah, I filtered it.
You filtered it, right? You filtered all of that carbon out. And then after you filtered, you made sure you had no solid. You acidified it, right? Now, bless you. So we did something instead to make it red.
Question. So for these labs that they test this on, would they give us some background info on it?
Yeah.
Or would they like?
No, they would give you, but it would be like this. Like what would happen if you didn't filter? Then you'd have some impurities, stuff like that.
So it's like, so you don't even have to know nothing about the lab pretty much. You just have to like know simple.
Yeah.
Simple stuff.
Yeah, like you just need to know like lab techniques. And I'll actually show you. This is what your crystals were supposed to look like if you did it in an ice bath. This is why we let it go overnight.
I don't like that.
What is that?
That's cocaine.
That's embarrassing. Like, is it candy?
Yeah. Alright, we gotta get over.
See what's going on?
Bye.
See ya.
Okay, and then after the AP test, you guys are actually going to synthesize aspirin.
Will they ask us about that on
No.
the test?
No. Okay, titrations, another big one. Different types of indicators. We talked about how to know what indicators to use. Typically, we use phenolphthalein, pH of 8 to 10. It turns pink at the end point. So there is a difference between end point and equivalence point. It's definitely important that you know the setup for a titration, which I really hope because we've done how many of them. One assumption that people make is that the end point is the equivalence point. That's not true. If you hit the end point, which is when the color changes, you went too far. That's why when we actually did the titrations, you had the lab quest, so you actually could see where your end or where your equivalence point was. If you would have waited until the phenolphthalein turned pink, you would have gone too far. So some sources of error, maybe you went past the end point, so you'd have too many moles. If you didn't read it right, okay, then your moles would be too low. Always, it's proper lab technique to rinse the burette with whatever's going in the burette first. So you pour some in, swirl it around, you pour it out, you pour some in, you swirl it around, you pour it out, then you fill it up all the way. So looking at these shapes, right? So here you can see where the end point is, the different types of acids and bases. What is the importance of the half equivalence point? pH equals pKa. Okay, so here's one. The graph below is a titration of a weak base with hydrochloric acid. Based on the graph, which point would represent the region where the pH is dominated by the molarity of the HCl being added? Okay, so you kind of have to think about what this is saying. Which point would represent the region where the pH is dominated by the molarity of the HCl being added? So HCl is what kind of acid? Strong. So we want to find where the pH more or less represents the pH of a strong acid. It's going to be E. Where would the equivalence point, around where would the equivalence point be? D. Yep. What about the half equivalence point? Yep, B. Right where it levels off a little bit. Okay, then redox titration. I actually like this slide a lot, just with all of the information that's on it. This is a great graphic, acid-base titration versus redox titration, because they are not necessarily the same thing. In an acid-base titration, obviously we use acids and bases. In redox, we're using oxidizing agents and reducing agents. In acid-base, we're focused more on neutralization versus oxidation reduction. Sometimes you use not sometimes, you always use weak acids and weak bases as indicators. Every indicator is actually a weak acid or a weak base. And usually the redox species, Ethan's not in here, the redox species act as their own indicator, changes colors. Acid-base titrations are usually more common. Redox titrations actually are normally seen among the D block elements, transition metals, like Mn. Applications of redox titration. There's one lab we didn't get to, but I had you guys just titrate hydrogen peroxide instead of orange juice. But you could actually determine the content of vitamin C, because vitamin C is just in ascorbic acid. And so you can actually do a redox titration in order to determine the content of vitamin C in some orange juice. And then two very common redox titrants would be potassium permanganate and potassium dichromate. We don't use potassium dichromate as much because it's expensive. Potassium permanganate is cheaper. Okay, we never used a potentiometer when we did a titration, nor do they require you to know, but just know that this technically could be a setup for redox titrations. You probably won't see this though. Okay. Normally we would use something along the lines of an indicator, like itself, permanganate. Sometimes you can use starch. Starch actually changes color with iodine. And then kinetics. We're going to talk more about this tomorrow. We're probably going to do a clock reaction. Well, yeah, except for first period. You guys will have to come in like during your study hall or something to see the clock reaction. But a clock reaction is something that actually delays its change because the mechanism is so slow. So we'll actually look at a clock reaction tomorrow. But we use spectrometry or colorimetry, and we looked at the change in color. So it goes from really dark to really light over time. We looked at the types of orders of reactions. So 0 order, 1st order, 2nd order, based on what your line is. Absorbance versus time, ln versus time, 1 over versus time. We'll talk about that tomorrow. You can find the rate law from the graph. You can also find the rate constant, lowercase k. You can also find the activation energy. We're going to look more at this data tomorrow, but the biggest thing is looking at concentration or absorbance versus time. So looking at kinetics, which of the following would increase the rate of a chemical reaction? So which of these would speed up the rate of a chemical reaction? So if you wanted to mess with temperature, what would you have to do to speed up the rate of a reaction? Increase the temperature. So we can ignore A. Products. If we're looking at changing the concentration of product, is that going to cause a forward reaction to occur or not at equilibrium? No. So we have to look at, we always want to look at reactants. Right? When you look at concentration, look at reactants. So what should you do to your concentration of your reactants if you want the reaction to move faster? Hey, you want to increase them. Remember, collision theory, you want them to collide. You want them to collide much more. The faster and the more they collide, the faster the reaction will occur. And calorimetry we talked about today, coffee cup calorimeter, most common. Application, specific heat of a metal. Heat of reaction, energy content of food. We don't use bomb calorimetry because they're very expensive. They're actually like metal containers.
For the last question, does that like not apply to like L'Hopital's principle thing? No, that's Cal. Wow, I am not in the right mentality right now.
I was like,
that's,
what?
That's what is it?
Le
Chalier.
Yeah,
It's a French dude. I know.
I was like,
Does that
who?
not apply? Yeah,
I missed.
I'm sorry.
I was like, yeah,
My question is relevant. My question
Le
is
Chatelier.
Yeah,
Kinetics normally is not an equilibrium count.
Okay, so that doesn't apply.
Yeah.
Okay.
So kinetics will be a single arrow, so you won't have to worry about Le Chatelier. It's like,
or L'Hopital's. Okay.
But you guys did both of these. You found specific heat. You did heat of reaction. We didn't do energy content of food because, again, we don't use bomb calorimeters. Some assumptions that we make, though, is that all of the heat stays in the coffee cup. It's not a great assumption because some of the heat does go into the coffee cup, and we don't have our lids sealed on all the way, so some heat escapes. But for us, it works just fine. But we do need to take into account coffee cup calorimeter constant. So when we find Q reaction, it's actually C cal delta T plus MC delta T. And then the only difference between Q and delta H, Q is only joules, delta H you divide by the moles of reaction. By qualitative analysis, not sure how much you have to know for this, but we'll do it. Metal ion flame tests. You did these flame tests. If we need to do them again, I'll see if I can make the solutions and we can do them again. Lithium is red, sodium is orange, copper is blue-green, it's like teal. Barium is bright green, potassium is purple, bright pink.
Oh, lithium was like a really bright.
Potassium was purple.
No, there was like
I remember.
Lithium.
We did it with Kelsey.
Maybe lithium. You think lithium may have looked bright pink?
It looked bright pink, but then you
Strontium
told
is
us
bright
later it was like
red.
red.
Yeah. I would say the big ones here to know: potassium, sodium, copper. It's probably maybe calcium is orange. So like sodium's like a yellow orange and calcium is orange.
This is so stupid. Why would that?
The biggest thing with this though is knowing why you see them, actually. Okay, and you see these because of electrons. So if you can see this color, what part of the electromagnetic spectrum does it fall in?
Visible.
Visible,
That makes sense.
right? So you can see visible light. And so the electrons jumping and falling, that's in the visible spectrum because you can see it. So that's going to be your flame test. In terms of KSP, remember the lower the KSP, the less soluble the substance. Low is like times 10 to the negative 12 versus times 10 to the negative 3. Okay, negative 3 is bigger than negative 12. So you can actually rank substances based on their KSP, and that would actually be the order that they would precipitate out. The one that has the lowest KSP is the one that's going to precipitate first because it's not very soluble.
Do they each have the same anion to compare them? Or can you
Not necessarily same anion, but you would want it to be the same ratio. So what I mean by that would be like barium sulfate, calcium sulfate, magnesium sulfate. It's all 1-to-1. Or barium hydroxide, you know, something that would then be 1-to-2. Yeah. And then this is just looking at precipitates. You used to have to know this. We don't really think that you have to know it anymore because all you have to know are the solubility rules: potassium, nitrate, ammonium, sodium. They don't make you know that everything else. What they might ask you though is, here's a list of something, 5 substances, here are their KSPs. What would precipitate out first? What would precipitate out second? What would precipitate out third? Something like that. Where you're actually applying KSP to a scenario because they're all about now not just memorizing. You used to have to know that PBI2 was yellow. You would have to know that, like carbonates were usually white. You'd actually have to know all of the colors. Yeah, why? I don't know. That's why they changed the test now.
If you
You're
found
not.
on the street, that would
Yeah.
be
you're not memorizing as much anymore, you're actually applying it. So you're applying KSP to a scenario. And then there are these little virtual labs that go along with it. Yeah, so you'd have to know like iodine would be yellow, bromide would be like a little bit lighter yellow. You don't have to know that anymore. Oh, we're not doing these.